Welcome to our iRay seminar. I have the great pleasure of introducing our speaker today, who is Jascha Sohl-Dickstein. Jascha is a senior staff research scientist at Google Brain and leads a research team with interests spanning machine learning, physics, and neuroscience. Recent projects have focused on the theory of over-parameterized neural networks, meta-training of learned optimizers, and understanding the capabilities of large language models. Jascha was previously a visiting scholar in Suraj Gunglali's lab at Stanford and an academic resident at Khan Academy. He earned his PhD in 2012 in the Redwood Center for Theoretical Neuroscience at UC Berkeley. And prior to his PhD, he worked for several years at NASA on the Mars exploration rover mission. Well, that's something much more interesting than I've ever done. So cannot wait for his talk today, which is entitled Learned Optimizers, Why They're the Future, Why They're Hard, and what they can do now. Jascha, I yield the floor to you.
All right. Thank you so much for inviting me, and thank you, Michael Kopp, for hosting me. Before I start, I should say I'm going to talk about a lot of work done by a lot of people, and I'd especially like to call out the ones shown here: Luke, Niru, and Daniel, and Jeremy, and Roxy. Luke especially is the person primarily responsible for most of the things that I'm going to be talking about, so he deserves a lot of the credit. I'd also like to very strongly encourage you to interrupt me to the degree practical with questions during the talk. Especially when giving a remote talk, like any kind of feedback I can get from the audience at all is a major service you can do for me. So I'm going to talk about learned optimizers, part of the future, why they're hard and what they can do now. The structure of the talk is going to be something like this. I'm going to talk about why learned optimizers are going to change the world. I'm going to tell you what a learned optimizer is. Then I'm going to walk through a sequence of practical challenges that we currently face trying to make these things work. And in a few cases, I will show some solutions. And then I'm going to show what they can nonetheless achieve now. And finally, I'm going to share a code library that we just released, which I highly recommend if you want to explore this area in your own research. Okay, so to motivate this, you can maybe tell the story of our present deep learning revolution as researchers used to learn features and researchers used to hand design features, and for a very long time the hand design features worked much better, and people built entire careers out of, for instance, hand designing features for image classification.
Jascha, I think are you intending to share your screen? At the moment you're not sharing.
Oh, did my screen not being shared?
No, it's I can't see it at the moment, at least.
Okay. Give me a second then. Yes, I had in fact been intending to share my screen. I guess it got unshared during the cool. Okay. All I said was the outline's going to look like this, but I said it verbally. And so now we're talking about motivation for why you might imagine that meta-learned algorithms are going to change the world. And maybe to start with, people used to hand design algorithms, and people used to hand design features and functions, and people used to learn features and functions. And for a very long time, learn features and functions did slightly worse. And then circa 2012, we started having learn functions outperform hand design functions. And after that, no one has a career hand designing functions for image classification anymore. And maybe the lesson here is that I'm hearing a bit of an echo as well. Maybe the lesson here is that given enough data and compute, that learn functions will be able to outperform hand design heuristics, even if those hand design heuristics are seemingly very well motivated. But we still hand design our optimizers and our loss functions and our architectures and our regularizers. And even when these are well motivated, they share the same characteristic that enabled learn functions to outperform hand design functions for classification, which is that they are really just heuristics. And if you have enough data, enough compute, you can do something better than a heuristic. Maybe to like motivate that concretely, if you're writing a paper about image classification, you probably want to report something like 0 or 1 accuracy on the test set. But you're probably training your model on cross entropy on the training data set. So even if you're using the most theoretically justified optimizer that there is, you're using it to minimize the wrong loss on the wrong data set. And it's really nothing besides a heuristic. And so maybe the hope of the current meta learning work is that we are poised on the edge of a similar evolution, whereas scales of compute and scales of training data, which in this case a training data point is like an entire task that you want to do better on, are growing large enough that learn functions will once again outperform hand design functions. Cool. So that is why I think that meta-learned functions or meta-learned parts of the machine learning pipeline are likely to take over. We're going to talk specifically about learned optimizers here. So diving in, let's look at what a learned optimizer is. So in optimization, you have some parameters, trying to call the inner parameters of a model. So you have some model you're training, and it has some parameters, W. And maybe you optimize your model by performing steepest gradient descent. You say, okay, my W at time step t plus 1 is going to equal my W at time step t minus some learning rate alpha times the gradient of my loss function. And you do this over and over and over again. And after you do like capital N steps of gradient descent, you measure performance. You look maybe at the validation loss or the test accuracy if you're going to put it in the paper. In learned optimizers, what we do is we replace this hand design mapping between W at t and W at t plus 1 with a learn function. So here we've replaced it with a learn function u, which takes as input the current value of W and the current value of the gradient of W, and really any other information about the problem that you want to pass it. And also has its own outer parameters, theta. And then it takes all this in and it spits out the W at the next time step. And you once again apply the learned optimizer over and over and over again until you've optimized your problem. And then in an outer training loop or a meta learning loop, you update theta. So you take the final measure performance and you say, okay, how could I change the hyperparameters, the outer parameters of the optimizer, so that if I were to run this optimization again, I would do better. And you update data over and over and over again. And so this outer loop is like outer training or meta training. And it's where you learn the parameters of the optimizer. And this inner loop, you take a learned optimizer and you apply it over and over and over again in order to optimize a target loss function of your choice. Okay, so this is the basic picture. We're going to replace the optimizer updates with a black box function with its own parameters. There's a lot of flexibility in terms of how you choose U, but just to have something concrete in mind, one very common choice is to have U be a per parameter function, often an RNN or an NLP. So what that means is that for every parameter, in your W. Every parameter in the loss that you're trying to train, you have a little independent copy of your learned optimizer. And so every little parameter has its own RNN that takes in a bunch of scalar gradients and spits out a bunch of scalar delta W's or changes in the parameter. You can think, by the way, of like atom or SGD with momentum as fitting into this framework as well. So for instance, with SGD with momentum, you can view that as like an RNN where you get a bunch of gradients as input, and your momentum accumulator is like the hidden state of the RNN. And then you'd have a linear readout of the hidden state, which produces the delta W, the change in the parameters. Okay, so I've told you why I think learned optimizers are going to change our small part of the world. And I've told you what a learned optimizer is. Now I'm going to talk through a bunch of reasons why training these things, outer training these things, is exceptionally difficult. And we'll try to present a few solutions. So the first problem is that optimization dynamics are often chaotic and extremely sensitive to the initial state and the parameters of the optimizer. And this leads to the outer loss that you're trying to minimize, the loss that you're trying to like descend in order to train the optimizer to also be like extremely chaotic, with like a lot of high frequency structure and exploding outer gradients. And this makes it very, very difficult to minimize and navigate. To make this more concrete and visual, here what we're going to do is we are going to train a 3-layer MLP using Atom. So there's no learned optimizer here at all. We're just going to train an MLP using Atom, and we're going to do a grid search over learning rates. So I don't know if you can see, but the learning rates here differ only in their third significant digit. Like we're exploring learning rates between like 0.1469 and 0.1484. So what we're going to do is we're going to instantiate a bunch of identical copies of the network we want to optimize, and then we're going to pass it mini batches in identical order. And we're going to train it with a bunch of optimizers where the only difference between the optimizers is that their learning rate differs in the third significant digit. And you start this, and initially all the optimizers move in, all the optimizers move the MLP parameters in almost identical direction. Here we're showing a PCA projection of the MLP parameters. So this is the way in which the parameters of the MLP are evolving. But after only like a dozen-ish iterations, you see that the actual parameter trajectories taken during training begin to bifurcate until after you've done like 100 iterations of training, this like change in a third significant digit of the learning rate has led to a completely different setting of the beginner problems parameters. So like infinitesimal changes in the learning rate can lead to very large macroscopic changes in the actual optimization trajectory taken. Was this picture clear? I will assume, yeah.
It's amazing.
Okay, cool. All right, so this though is just what's happening to the inner parameters. What we care about is actually the outer loss surface. And so it would be possible, for instance, that maybe these trajectories here and these trajectories here have exactly identical outer loss, in which case this would not actually be a problem. So we can look at the same thing, but we can look at it in terms of the outer loss surface rather than in terms of the inner parameters. So here, what we're doing is we're visualizing. In this case, we're applying a learned optimizer. In this case, we're trying to use a learned optimizer to once again optimize a small network at MNIST. And here, what we're showing is a 2D slice through the parameters of the learned optimizer. And here, intensity corresponds to meta loss value. So if you want to outer train your optimizer, then you want to navigate from bright regions to dark regions in this image. And you can see that initially this image looks very, very smooth if we only apply the learned optimizer for one training step. But as we increase the number of enroll steps, as we increase the number of steps that we apply the learned optimizer before we measure the meta loss, then you see that the loss landscape becomes increasingly complex after even a very small number of steps. And we can keep on going, and the complexity will continue to increase until after applying your learned optimizer for just 50 steps of training, you will end up with a loss landscape which is like so non-smooth that basically every pixel in this image is discontinuous, has a different value than neighboring pixels. Trying to descend this loss landscape via steepest gradient descent will be completely ineffective. You'll descend in an essentially random direction with gradients that are like around 10 to the 30 or something, and you won't be able to do anything. So okay, this is the first and possibly actually the most significant blocker to training learned optimizers. How can we fix it? I can show you a solution which works, although it is like really wastefully costly. And that solution is that we can smooth the outer loss landscape. If you look at this previous image, you can see that actually for reasons we don't fully understand, the chaotic structure of the loss landscape it's only chaotic like spatially locally. So if you could imagine like blurring this loss landscape, then you would have a like well-defined smooth landscape that you could descend. And so that is exactly what you do. You take a distribution over the parameters, which is just taking the current parameter value and adding a bit of Gaussian noise. And you replace your original loss function with a loss function here, fancy L, which is what you get if you average over all these small perturbations of parameters. So this is the same as like smoothing the loss landscape or convolving the loss landscape with this Gaussian distribution. And then we can optimize fancy L instead of L. This is fairly effective, except that computing the gradient of fancy L is somewhat challenging. So as a bit of a detour, we can ask, how can we compute the gradient of this thing through the expectation? There's maybe two obvious ways that you could do it. One of those ways is that you can use a reinforced style gradient estimator, where you replace the gradient of an expectation of a loss with the expectation of the loss times the gradient of the log distribution. And if you do this, you get something called the evolution strategies estimator for the gradient. You can actually derive it in like 2 lines. I actually, just before the talk, removed a couple build slides that did it because I thought it took too much time, but it's a super short derivation. And You can think of ES maybe as if you want some intuition for it, as computing the gradient by estimating the correlation of the change in loss after a perturbation epsilon is applied to it with the perturbation itself. I've written ES in a slightly unusual form, which is I've written it explicitly in terms of a pair of antithetic samples, where you don't just, where you take the difference of L of theta plus epsilon and L of theta minus epsilon. I've done this maybe for two reasons. One of those reasons is that if you want to get any kind of reasonable gradient estimate out of ES, it's absolutely crucial that you use antithetic samples. They cancel out the leading term in the variance of the estimator. So you get many orders of magnitude lower variance if you do this. The other reason is I think writing it this way makes it very clear that ES is just a stochastic finite difference estimator for the gradient. We're choosing the direction and we're measuring a finite difference in the loss in that direction, and we're using that to build an estimate of the gradient. Okay, so ES is one of the techniques we can use. The other technique that you can use to compute the gradient of this thing is to use the reparametization trick, where you can rewrite this expectation over theta tilde in terms of theta as an expectation over epsilon drawn from this distribution of L of theta plus epsilon. And then you can take the gradient of that, and it will just be an expectation of samples from this distribution of the gradient of L. So these two different methods of computing the ES gradient have dramatically different variance properties. The reparameterization gradient is nice because you're taking an analytic gradient. So if your loss surface is smooth, then the analytic gradient will have lower variance and will be much more efficient. Whereas if the loss surface is smooth, the ES gradient is like a stochastic difference method. It's going to be high variance and it'll be kind of crappy. On the other hand, if your loss surface has a lot of high frequency structure, if it's very high curvature, as meta learning loss surfaces often are, then the ES gradient will continue to be kind of crappy, but it will be just as crappy as it was before. It won't be much crappier. Whereas reparameterization gradient might move from 5 orders of magnitude better than the ES gradient in terms of variance to 20 orders of magnitude worse than the ES estimate in terms of variance. Here, what we're looking at is we're looking at training a learned optimizer, and the x-axis is number of inner problems trained. So it's like compute time for training the learned optimizer, and this is the gradient variance. And you can see that early in training, reparameterization gradient is way better, and then later in training it explodes, and the ES gradient remains roughly the same throughout. This also illustrates maybe another phenomenon which is important, which is that it's not just that there are regions in the meta loss space where optimization trajectories are chaotic. It's not just that there are hyperparameters for which optimization trajectories are chaotic. It's that very often the best performing optimizer is one which is balanced on the edge of chaos. You can see this even if you're just tuning a learning rate. Typically the optimal learning rate is the learning rate right before your model diverges over the course of training. And so it's not just that you have to worry about chaos in your outer training. It's that your outer training is actively attracted to regions with chaotic behavior. Cool. Okay, so you have these two separate estimates of your smooth loss function. You can combine them. One way to do it might be like theoretically justified might be like to do like inverse variance weighting, to take like a interpolation between them. Although in practice, like one or the other of these terms is going to dominate by many orders of magnitude. So really, you would just choose whichever one is most helpful at a given point during training. Okay, I'm gonna pause here for like 5 seconds in case there are any questions.
Are there any questions at the moment? I don't see any. It's very captivating, Jascha.
Okay, cool. So I've told you that learned optimizers are going to change a little bit of the world. I've told you what they are, and I've told you one of the reasons that they're challenging, which is that the loss landscape you need to navigate to train them is horrific. Another reason that they're challenging is it may be much more mundane, but just as challenging is that they're extremely expensive. For instance, if you think it takes capital N steps to train a model, where maybe capital N is like, I don't know, 10,000, then now for every step of training the learned optimizer, you need to also, if you do this naively, spend capital N steps training the inner model in order to get a learning signal or a gradient for training the learned optimizer. So your compute cost goes from like, at least naively, order N to order N squared. And that's not even taking into account the increase in the compute costs that comes from using a stochastic difference method rather than analytic gradient for computing your update directions. So these things can be atrociously expensive. There's a few solutions to this. One of the solutions is to work at Google and just run things on 10,000 machines. One of the solutions is to make really clever use of vectorization hardware and accelerators. So for instance, you can do maybe surprising things like if you're applying the same learned optimizer to many tasks during training, you can vectorize over the tasks that you're applying it to, which can lead to a great deal of compute. Another solution, which is almost required, is to use partial enrolls rather than full enrolls of the inner problem. This is the same thing that is done, for instance, when training RNNs over very long sequences. Partial enrolls come with their own difficulties, and going to talk about persistent evolution strategies as a way to address some of those difficulties. So this is just a diagram showing you what it means to break a problem into a sequence of partial enrolls. And what it means is that rather than running the entire inner problem before computing an outer loss and a gradient, you instead run the inner problem for some small number of steps. You compute an outer loss and a gradient here, and you update your outer problem, and then you continue to unroll the inner problem for another small number of steps, and you do it again, but you completely neglect the component in the gradient that captures interactions between these enrolls. So this is very nice in that you get many more gradients. It's also very nice in that you end up descending a much smoother loss surface. So you remember from the progression earlier that the larger the number of steps that you unroll optimization, the more chaotic your loss surface is. So you can actually also get a nicer loss surface to descend by backpropagating through shorter enrolls. The cost of this approach, though, is that it's biased. We're neglecting the contributions to the gradient that if you're doing backprop, that would come from like backpropping across multiple unrolls. So more specifically, this bias often leads the optimizer to be overly conservative and as a result make very slow progress. There's a really nice paper by Wu and Ren et al. That dig into this, but they provide a toy example, which I think is a very informative one. And so here you can imagine that you're descending a ill-conditioned 2D Gaussian, and you're getting noisy gradients. So you have a Gaussian, which is like high curvature in the y direction and low curvature in the x direction. And then the gradients you're getting have some noise added to them. And in this situation, if you want to make good long-term progress, then what you want to do is you want to set a large learning rate. And what a large learning rate will allow you to do is it will allow you to move farther along the low curvature direction. But the cost of having a large learning rate is that the noise in the gradients is going to lead you to have a very large contribution to loss along the y-axis, along the high curvature direction. On the other hand, if you are instead trying to descend this loss landscape as quickly as possible in a very small number of steps, you're better off setting a small learning rate, and that small learning rate will allow you to rapidly converge along the high curvature direction, but will cause you to make only very slow progress in the low curvature direction. And so as a result of that, if you are optimizing using partial enrolls, you're basically saying, let's do as well as possible in this like short amount of time in the immediate future. And the way you can do as well as possible in that like immediate future is to make your learning rate very low and descend along the high curvature directions. And so this leads you to be overly conservative. You can see this in terms of the learning rates that you get if you do meta training as well. So here we are using Atom to train a 2-layer MLP on MNIST. And we are using our meta training infrastructure to learn the log learning rate of Atom. And we're doing this for a variety of truncated enroll lengths. And you can see that if you truncate, you split the optimization up into a bunch of short enrolls, that you learn a much smaller and more conservative learning rate. And as you increase the enroll length, then the learning rate gets more and more aggressive and becomes better and better performing. Okay, so this is the problem of bias. I'm going to tell you briefly about a solution we have to this, which is a technique called persistent evolution strategies or persistent ES. In PES, you split the computation graph into a sequence of shorter enrolls, and you perform an ES-style parameter update after each one of those enrolls. But unlike in ES, you also accumulate a correction term, which captures the dependence of later losses on earlier enrolls, and allows you to eliminate the bias. And it's pretty cool because it allows you to do a sequence of rapid outer parameter rates updates to your optimizer. It's eventually unbiased, meaning that if you run, after you run all the unrolls and run to the very end of the inner problem, your gradient estimate you get from the entire process will be unbiased. And it has also the nice properties that we already like from ES. The biggest one being that you descending a smooth version of the loss surface due to the Gaussian perturbations, and additionally, because you're not doing backprop, you have much lower memory cost. You only have to run the thing forward. I'm going to take a minute to just really briefly look at the algorithms for ES and NPES and highlight how they're different. So in ES, you compute a gradient estimator by drawing a Gaussian perturbation or flipping the sign of the Gaussian perturbation from the last time step in order to do antithetic samples. And then given that Gaussian perturbation, you unroll your inner dynamics, which in this case means you apply your learned optimizer with perturbed outer parameters, theta plus epsilon instead of theta. And you compute the loss after that unroll. And you add your perturbation times that loss to your gradient estimator. And since the ES estimator is essentially just the correlation between the change in the loss and the perturbation, this is it. This is the way in which you compute the ES estimator. The only other step is a normalization. In persistent evolution strategies, you do something very similar, but you initialize this accumulator chi as well. And after each unroll, you add the current perturbation to this like accumulator of perturbations, and then you just take the correlation between the accumulated perturbations and the loss rather than between the single enroll perturbation and the loss. So it's a pretty lightweight change. And it does, in fact, solve a significant portion of the bias problem. Here we're showing a plot where we meta-train a learned optimizer on a two hidden layer MLP and CFAR10. And you can see that ES, when you train it using partial unrolls, settles to a suboptimal meta loss value, while PES is able to find much better meta losses and is also, for reasons actually we don't fully understand, also more consistent across random initializations. Okay, cool. So I've shared two problems with somewhat satisfying solutions. One of those problems is that the loss landscape is like incredibly chaotic, so you have to smooth it. But solution's not fully satisfying because smoothing the loss landscape requires using a finite difference estimator, which is like much more expensive. Second problem we've talked about is compute cost, and ways to deal with compute costs mostly involve performing shorter enrolls. Shorter enrolls are bad because they're biased. You can correct for that, although once again you're using a finite difference estimator, which is an inefficient way to compute gradients. There's maybe one more major problem. Looks like you want to have a question. Oh no, okay.
I would have a quick question actually.
Yeah.
So do you, so the dimensionality of your theta, so that's the parameters for the outer loop, given that you then choose this standard deviation or the for your epsilon variable. If that's so, if you go to the algorithm, it's actually perfect.
If I go to which, say it again.
Or the algorithm or the slide before, yeah, here. So I mean, do you not? I mean, if it's high dimensional, so theta lives in a high dimensional space, you're essentially sampling of a sphere, right, by the curse of dimensionality. So this sigma you have is somehow for your outer loop is somehow like a quasi learning rate as well, right? If the dimensionality of theta goes up, how do you determine that sigma?
Yeah. So sigma is it's a hyperparameter that we tune. We typically set it to a constant. We've actually experimented with trying to come up with scaling rules with dimensionality, and none of them have worked better than like setting it to a constant and then like tuning it a little bit.
But
But
but what dimensionality does your theta currently have, and how do you choose?
oh yeah, great. Yeah, so it depends. Theta will often be tens of thousands of parameters in our current learned optimizer. Um, I so one concern that I think you're getting at, which is a huge concern, is that like finite difference style estimators are going to have a variance that like scales linearly in the dimensionality of the space that you're trying to optimize. So it seems like it would be badly suited towards training in high dimensional spaces. There's maybe two things I can point out that might partially address that concern. Maybe one of them, which is completely unrelated to learned optimizers, is I don't know if you're familiar with this like work on like intrinsic dimensionality by like Jason Nielsen or Zan Liu and some others. But there, the maybe surprising finding is that if you take a high dimensional neural network and you choose a random subspace and you optimize only within that random subspace, that you can still do quite well, even if that random subspace is like orders of magnitude lower dimensional than the like ambient dimension, than the true dimensionality of the parameters. And so I think one reason we might be somewhat okay is because it may be that like the intrinsic dimensionality of these learned optimizers is lower than the actual parameter count. There's another reason that we might be okay, and that other reason we might be okay is because although this is a high variance estimator, it has one very special property, which is that the sign of the gradient comes from this like finite difference measurement of the loss. And so this means that while the gradient will be very high variance, it always points in a downhill direction. Like the inner product of based from a single sample, the inner product of GES, or the inner product of GES with a true gradient is always going to be positive. And the reason for that is because if it was negative, then this would have the opposite sign. And so that maybe makes this like a less harmful, you're never going to go uphill. It's maybe a less harmful version of variance. It's a really good question though.
Thanks very much. There's another question.
I think you already mentioned it. You often optimize in a low-dimensional subspace, but it was even found out that you do a couple of steps in a high-dimensional space, and then afterwards remain in the low-dimensional subspace. There's a couple of papers out now. What's your comment on that? But I mean, perhaps this estimator works after you do a couple of steps, and if you settle down in this low-dimensional subspace, it would work.
Yeah, I think it's a great idea. I think maybe what you're suggesting is you want to like take lower variance steps at the very beginning of training, and then like relax to the PES or ES style estimator. I think that would be a really good thing to try. We did that a little bit maybe with the reparametization gradient style work, where this green line is an analytic gradient estimator, which works well early. Maybe one thing, I think the behavior you see where you have like a massive rearrangement of like the kernel of the neural network, like early in training, and then it stays constant late in training. I think that is often behavior you see as the neural network gets quite large. It may be that our optimizers are so small that we don't benefit from that kind of like stabilization effect, but I'm not sure. It's a good question.
Thank you very much.
Cool. Okay. So I've talked about two problems. There's a third problem, which is maybe more mundane, but just as important, which is how do you get these things to generalize to new tasks? Like we really would like an optimizer that we can apply to anything and have it just work. If you're doing standard supervised learning, you probably need like, I don't know, at least tens of thousands of diverse training examples before you can hope to generalize reasonably to a test set. And so we probably need something like that for optimization. But in optimization, each example is not like a data point. Each example is like an entire task. It's like an entire model that you have to train. So the solution to this is perhaps straightforward, but also requires a really remarkable amount of work. I would like to call out Luke again here, which is you need to just grind through and build a very large data set of diverse optimization tasks that you can use to meta train your optimizer. This is an embedding of such a data set. Perhaps reassuringly, these do what you hope, in that as your outer training set size increases, as you train your optimizer on more and more tasks, the optimizer does better on held out tasks. So this both validates that this is something we need to do, and that we probably need to keep on doing, but it is something that we can solve. There is, though, maybe one aspect of generalization which you can't fix just by increasing your training set size, and that is generalization to larger problems, and that you really like the learned optimizer to work for problems with like
a question.
Yeah.
You're talking about tasks, but your tasks are properly associated with models, model structure, model architectures. Is it tasks or is it different model architectures?
Yeah. It's even more than that. So when I say task, I mean the combination of the model architecture, the training and validation data set, the loss function on top of the model architecture, and I think those three would be the primary ones. So it's like all three bundled up together. This does though, I mean, you can kind of, this does make it slightly more efficient to explore the space, because you can kind of do an outer product of like data set versus like architecture versus like loss function to generate more diverse tasks.
I have a related question. I saw that already having like 200 or 300 of these data points, task data points, is enough to give quite good generalization accuracy. And I was wondering, I guess these are randomly subsampled from the set. And I was wondering if you purposefully chose a subset to cover this variance, could you maybe even get away with fewer, get away with fewer?
Yeah, it's almost certainly. These are not.
How do you choose them? from
yeah. So here they're chosen randomly. There's the flip side to that question though, which is like this is showing performance on an IID test set. And what you probably really want is you really want the optimizer to do well when you apply it to some new problem that doesn't look like any of the training problems. So you really want it to perform well under like domain shift, whatever domain shift means for like optimization tasks. And there it's even harder. but we've just been doing like IID sampling of training data. Cool. Yeah. Okay. So you can't. So you want your optimizer to work on problems with like billions of parameters. You cannot, for compute reasons, like meta train on problems that have billions of parameters, and so generalization across scale can't rely on like generating a meta training set that like looks like the large scale problems, but by being large scale itself. And this is actually an area where we struggle. This is maybe a completely open problem, which is how do you get these things to generalize effectively to very large scale tasks. The next section is going to talk a little bit about how you can design learned optimizers with like the right inductive biases. Inductive biases are important, like for vision, like CNNs and convnets and the like, or for text like transformers. Like finding the right architecture is central to these things working well. I'm actually going to skip through this in the interest of time, and let's get to the good stuff, or the more fun plots, which is what can learned optimizers do now. To be completely concrete about what we're going to do here, we are going to find the parameters theta of the learned optimizer that lead to the best performance on a distribution of tasks, or in this case, that distribution of tasks is going to be 10-way classification problems sampled from like downsampled ImageNet, like 32 by 32 ImageNet. And for each of those tasks, we are going to compute our outer objective, which is either going to be training loss or validation loss, after applying the learned optimizer to the task, which in this case is training a small convnet on a subsampled problem from ImageNet. And lesson number one is, if you're willing to put a lot of compute up front and amortize it later to meta train a learned optimizer on a specific task, then learned optimizers can dramatically outperform hand design optimizers on that task. So here in red, you can see a learned optimizer which was trained using the training outer objective. And you can see that it descends even wall clock time much faster than the closest competing hand design optimizer. You should never trust people's tuning of hyperparameters of baseline methods, but I will say that this is, we tuned learning rate and both linear and exponential learning rate decay schedules, and beta 1 parameter and beta 2 parameter and epsilon parameter and L1 and L2 regularization coefficients over a little over 2,000 hyperparameter configurations for the like atom plus reg plus decay baselines. So these are actually quite strong baselines. A cool thing about learned optimizers is that you don't have to outer train them targeting training loss. So for instance, you can train a learned optimizer to minimize validation loss. And if you do this, you are able to train a learned optimizer that achieves a lower validation loss, or in this case, a lower test loss than any of the other optimizers. Maybe an interesting observation is it really is like doing something qualitatively different, because it is achieving the lowest test loss, but is also achieving the highest training loss. So it is being actively inefficient at training in order to do better at generalization. Another interesting observation is the learned optimizer and the highly tuned atom both show this property, that when they effectively descend training loss, they rapidly diverge on the test loss. So,
a question.
Yeah.
Now you show test loss things, but what is the goal of an optimizer? Should the optimizer only decrease the training loss, or do you expect from an optimizer already be good in generalization. Are these two parts, or do you want to already integrate into the optimizer some generalization capabilities?
Yeah, so I mean, I guess it depends what your research interests are and who you are. I think in practice, people don't tune their optimizers on the training loss, right? They tune the hyperparameters of the optimizer using validation loss. I think what people really want is an optimizer that trains a model that generalizes well. And I think learned optimizers give us an opportunity to build that generalization loss function like explicitly into the optimizer. So I think we usually want to target like validation or test loss, not training loss, but it depends.
But I would question this because I had once a student. He had a programming bug in his optimizer, and it led to regularization. Therefore, optimizers with programming bugs perhaps work better than correctly programmed optimizers.
Yeah, for sure, right? And probably. I mean, I guess it depends who you're trying to sell the optimizer to, but if you're trying to sell the optimizer to like a practitioner that wants to like train a model, then they would probably prefer the one with the bug, right? Like they would probably prefer the one that leads to the model to perform better. Cool. Okay, so what else can learned optimizers do? So when you ask them to generalize to new tasks, they can outperform hand design optimizers if the hand design optimizers have a limited hyperparameter tuning budget. So here, the x-axis is how much the learned optimizer outperforms a hand design optimizer. And here we're forcing, and this is over a distribution of tasks, where the hatched lines are from a held out distribution of tasks, and the solid lines are from the outer training distribution of tasks. And here we're restricting the hand design optimizer to use the single hyperparameter configuration that allows it to perform best across the full distribution of tasks. And so if you only give, if I tell you, okay, you can choose an optimizer to run on a new task, but you're only allowed to run it once with a single hyperparameter configuration, which you choose in advance, then learned optimizers will do better. As you increase the number of hyperparameter search trials that you allow the hand design optimizers to perform, then I don't know, somewhere between like 10 and 1,000, the hand design optimizers start significantly outperforming the current generation of learned optimizers. Okay. I talked about generalization to larger problems. Let me show you what that looks like. They do sort of okay, but not great. So here we're applying a learned optimizer to the MLPerf like ResNet 50 on ImageNet, and we're comparing against the like standard optimizer that people use there, which is Lars. And you can see the positive side is that the learned optimizer does better in terms of minimizing training loss and increasing training accuracy. The downside is here the dashed line is test performance, and the learned optimizer does significantly worse in terms of test performance. So you wouldn't actually choose the learned optimizer to solve this problem, but it's like starting to be in the running, which maybe wasn't even true like 6 months ago. So that's kind of nice. You can do a similar experiment where you optimize 125, where you optimize a relatively large transformer language model, and you see similar behavior where the learned optimizers, here's two different learned optimizers, where the learned optimizer descends the loss, but does not descend the loss quite as effectively as the hand design optimizer that's like been tuned for this problem. Finally, learned optimizers have reached a point where they can do something that's maybe really fun, although I don't know if it's yet practically useful, which is they can train themselves from scratch. So you can take a learned optimizer and you can apply it. You can give it gradients that come from PES or ES, and you can ask it to optimize the parameters of another learned optimizer, and it will do roughly comparably to Atom. So they're almost to the point where they can lift themselves up by their own bootstraps. I wanted to show you one more thing before I ended, and I know I'm really pushed at the end of time, which is we're in the process of it's now on GitHub. We're releasing code, research code base for learned optimizers that has optimizers and tasks and training algorithms, and which will actually enable you to train a small learned optimizer targeting a small task in like just minutes on an accelerator. This will take 2 minutes and 16 seconds, so I will let it run. So you can like define your learned optimizer architecture.
Take your time, Jascha. We're not completely strict with that, so please.
Okay. Well, I will go 2 minutes and 16 seconds over at least, and then we can discuss. Awesome. Okay, so you can define your learned optimizer architecture. You can define the task that you want to optimize. You want the learned optimizer to optimize. You can make some hyperparameters choices, like about truncation schedules. Number of tasks is basically the outer mini batch size. It's like how many tasks you do in parallel. You can choose a gradient estimator for your learned optimizer. We're going to use PES here. And then you can choose the outer optimizer, so that thing that takes in that gradient estimate and like spits out updates to the outer parameters. We're going to use Atom. And then you can initialize weights and unroll state. And then you have a training loop that looks basically the same as the training loop that you would get for a standard model. You just loop over training steps and you compute gradients and you apply the gradients. Here we're going to do a number of training steps, which is like outer mini batch size 16 times 20 steps of truncation length of 20, so 20 enroll steps, times 1,000 training steps, and then times two antithetic samples. So we're going to have like 640,000 inner training steps. And you can see we've run this. I think this one was run as on a GPU. And you can see this is now run in the video, and it took 53 seconds to train this learned optimizer, which is you maybe don't know how remarkable that is unless you've spent like days training these in the past or weeks. And here you can see the meta loss as this learned optimizer is trained. And we can now look at what this learned optimizer actually does on the training task. So here we're applying a learned optimizer to the training task. And here we're applying some baseline optimizers, which are just Atom with different learning rates to the same training task. And you can see that after 53 seconds of meta training, learned optimizer does as well as Atom, maybe slightly even better than Atom with a semi-tuned learning rate. Okay, and now we talked about generalization being a major problem. So let's look at how this thing generalizes. So we're going to ask it to do a different task. It's now going to do a MLP value network on fashion MNIST with a much larger network. And we're going to run it for many more steps. We're going to ask it to train for 1,000 steps. And I think the one above was for 100. And so now this is just applying the learn optimizer to that task. And you can see that, in fact, we fail at generalization because we've only meta trained on one task. And so you can see the Atom baselines do great on this new task, and the learned optimizer is now just a flat line. But the point is, we just ran an experiment with learned optimizers on a single accelerator in 2 minutes and 16 seconds. So if you're interested in this, I think this may be a software toolkit which makes it practical to start working with these things. So cool. So to summarize, I think we're poised on the edge of a revolution where basically every ham design heuristic in our model pipeline gets replaced with a learned function. I think one example of that is going to be learned optimizers. Learned optimizers still have a bunch of open problems. There's pathologies in our loss landscape. They're extremely expensive. We need to find the right inductive biases. We need to improve the generalization. We need to better understand what their mechanisms of action are. But despite that, they're starting to do things now. They can outperform hand design optimizers if you are willing to put a lot of compute up front on a narrow domain. They can generalize better than hand design optimizers with a small hyperparameter training budget. And they're getting better all the time. And there's a library out that you might enjoy. All right, thank you very much.
Thank you very much for a fantastic talk. Oh, please clap. Now that we're live again, we can do that. So yes, thank you. There are actually quite a few questions coming in, and I might have some as well. I'll start with the first one, and then I'll give it to the audience. Seb, you go. Yeah, and
then. To my opinion, what you're doing, you're looking at optimizers, but for me, like what's happening in the field, you get more package of what you call tasks together with an optimizer. You know, for instance, a task like ImageNet with ResNet 50, I use this optimizer and I have to tweak at sysnop or sysnop, stuff like this. It's not that the optimizer is so separated from the architecture, from the task. You get it as a whole package. Somebody figures out this fits good and others only turn a little bit. What's your take on this? Should really optimizers be separated from tasks, as you call it?
Yeah, I think you've identified like a super important continuum. I think my answer is like sort of yes, sort of no, and it depends. I think if you're going to perform like a very similar task many times, then it makes a lot of sense to put a lot of compute and work up front and to build something that's works really well for that task. I think though that you also want to be confident, at least if you're a researcher, that your optimizer will continue to work if you like change some aspect of the task, if you make it deeper or you decide to try a different nonlinearity or a different type of normalization or so I think you want them to be as robust as possible somehow without sacrificing performance. And I think there's like a continuum of trade-offs there between robustness and performance. And I think everyone probably wants to be at a slightly different point in that Pareto curve.
very nice. Maybe a corollary to that question. Do you think, would you want the optimizer to be aware of the layer structure or the computational graph behind it when training?
Oh yeah.
Compared to something like LAS, I mean, LAS kind of is aware, maybe on a convolution layer you want to do something else.
Yeah. So definitely, I would. A lot of the optimizers that work best are like, although this is for compute overhead reasons as well, are hierarchical optimizers where you have like maybe an LSTM running for the whole network, and then you have like a per tensor like LSTM maybe, and then you have like a per parameter like tiny optimizer piece. So that like building the optimizer to have structure that matches the problem structure seems to help a lot. I actually think it'd be really great to even have them optimizer like traverse the compute graph and like use an embedding of the compute graph. But that's a lot of work and no one has done it.
Very nice. Thank you. I have a question from Christian Eichenberger, who says, many thanks for the great talk. In one of your papers, you mentioned limitations of TensorFlow event files when doing summary aggregation at 10,000 summaries per second. Can you say more about the limitation of the file format? Is the problem the amount of data to be stored, or is it later query performance? More generally, can you share some learnings from the design of your analysis tool?
Yeah, so the details of this question would be better put to Luke Metz than me. I don't remember enough where the bottleneck was in summarization. In terms of the analysis toolchain, one thing I can say is our earlier versions of kind of learned optimizer work relied on like parallelizing things over tens of thousands of CPUs. We've more recently moved towards parallelizing things over just a handful of TPUs or GPUs we're fine too. And this actually So a lot of the struggles that we ran into in parallelization have been helped a lot by just leaning hard into accelerators. And so you'll see that in the toolkit, that it's like much smaller workloads running on accelerators. So I think like the summaries per second kind of problem is no longer there. But I think this question in general, Luke would be able to answer far better than I can.
Okay, that's very kind. Thank you. Any question?
Hi. So my question is, like, can you elaborate on how your learned optimizer is agnostic to the network architecture? Because like you need to be able to apply it to different tasks, right? So that was not clear.
Yeah. So you can so kind of under the hood, I showed you experiments with a variety of different learned optimizer architectures. But I think the simplest case is that you just have one copy of your learned optimizer running for every parameter in your target task. So the simplest case is if you have like if you go from having 1,000 to 1,000,000 parameters, and you just go from having 1,000 to 1,000,000 like independent copies of your learned optimizer, where each copy of the learned optimizer only sees the gradients and parameter value for a single parameter in the network. And that's, you can kind of imagine that's kind of the same as what like Atom does or SGD plus momentum does, right? Like SGD plus momentum, you can imagine you have just like an individual accumulator for momentum for every parameter in your network. And that accumulator only sees the gradients with respect to that parameter, and then it only outputs the updates for that parameter.
Thank you. Yeah, cool.
I'm allowed to ask another question. My budget is used up. One question where you add noise. From the early days, where the dinosaurs were outside, we had something which is called simulated annealing, which casts this as temperature, but the behavior is the same, that the error landscape flattens out, gets smoother, and with lower temperature, you get the thing. What is the connection of your techniques to the old, very old techniques like simulated annealing?
I mean, I guess the difference between this and simulated annealing is that we wouldn't anneal it. Okay, actually, I think in this case, actually, they're pretty different. I think there's two big differences between simulated annealing and this. Difference number one is simulated annealing. You don't do spatial smoothing. You instead, when you change the temperature, you basically change the like depth of the valleys and hills. So that allows you to move better if you're taking like stochastic steps. But if you were trying to do like analytic gradient descent, wouldn't allow you to move better. And the other part is maybe for us, it becomes more and more important that the loss landscape be smooth. The later in training it is. So if anything, we would do like the opposite, where we would like increase the noise in our smoothing function as we got later in training, and as the optimizer is like attracted to these like edge of chaos like solutions.
Thank you very much. I have a question from Yuan Cheng. Thanks for a great talk. One curious question. I think current coordinate-wise learned optimizer can only optimize small network. The intuitive reason is, as over-parameterized networks have millions of parameters, we may need comparable number of parameters in learned optimizers, I guess, in order to have enough complexity to approximate this optimization. However, a large learned optimizer on large networks to optimize could often lead to heavy computation and out-of-memory issues. How would you think the practical next step to make learned optimizers useful to large models would look like?
So I think this is maybe partially addressed with the answer to the earlier question, which is that there's like weight sharing essentially in the learned optimizer. So you can have a learned optimizer that's, for instance, per parameter, and you can apply it to networks of arbitrary size. There's also let me something I skipped, but which I'll now jump to is you can also imagine there's like some kind of like Pareto Frontier here, where the more complex your learned optimizer is, either the more overhead you get per optimization step, or the more overhead you get in terms of memory, because the optimizer needs to like store its hidden state across training time steps. And typically what you find is that the more complex you make the learned optimizer, the better it does, but also the more it costs. And in fact, here, the most costly learned optimizer is the one that does the best. But there are some architectures that are a pretty reasonable trade-off between compute and memory overhead and like performance.
Thank you. Another question from Christian, actually. Do you provide pre-trained learned optimizer as drop-in replacements for PyTorch or Tensorflow optimizers? How many task family dedicated optimizers would there be?
The answer to the first one is not right now. I actually I take that back. I actually think you can plug in the optimizers in the library as like Jack's optimizers. I guess they wouldn't be PyTorch or TensorFlow. How many task family dedicated optimizers would there be? I don't think I know how to answer that question. I mean, I think it's like I think it's a research area that you could. It's however many people choose to train, I guess.
Very nice. Any more questions from the audience? Your budget is infinite, so please. Don't be shy. Well, then I have one. So what do you think? I mean, you had the problems listed. What do you think is the next step, or where would you like to see learned optimizers made an inroad?
There's maybe two next steps. I think the biggest thing I would like to see, because I think it's the one that will maybe most compellingly convince people that these are a good idea, is I'd like to see us solve generalization to large models. Because I think if you can show a learned optimizer that does better at a large model, that is likely, like a large commonly trained model, that is likely to be one that's actually adopted. So I think that's maybe, for purely practical reasons, that's maybe a near-term target. I think there's a lot of open questions though. One of those is like we're throwing away analytic gradients when you train these things, and that's like clearly a bad idea. Like analytic gradients provide you with so much information. So I think figuring out how not to throw those away is eventually going to be incredibly important. I also think that generalization as a whole is not something that we really understand very well yet, and it's something that we need to. I don't know. There's lots of open problems in every part of this.
Brilliant. Are there any more questions? I think. Wait, let me check online.
Yeah, there's a question about whether learned optimizers work better for particular types of data, like images or text or video sequences. I don't think we've really explored that. A lot of our experiments end up being with images, I think just because we're kind of familiar with image models personally. But I don't think I don't think we've done controlled enough experiments to be able to say anything about it.
Brilliant. Well, if there are no more questions, I thank you very, very much for an amazing talk. Thank you everyone for participating. And I think we might go into a different room, Jascha, if you still have time. And
sure.
For the audience out there, thanks very much and join us next time. Bye-bye.
Thank you very much.